Okay, so this is my work for quiz number 2. And in this problem we have a car that's stopping on a road, and we're told the distance that the car can stop on a flat surface, and that's a distance of 50.3 meters. And we're also told the initial velocity of that, and then thinking about this we can know that the final velocity will be 0, and the initial position we can set to 0 as our starting point. And then we're asked to find the car's braking distance once it's going up a 2.7 degree incline. And we're told that it has the same starting velocity, and so we're looking for that distance. And so to solve this problem, I started by just looking at the car on the flat surface and trying to get as much information from that as I could. And so I drew a little picture of what was happening, and then I took that and drew a free body diagram from that. So we have the normal force up, the weight down, and then the force of friction from the tires stopping the car. And then that equals our kinetic diagram, which we're accelerating to the left. And then I put the direction for my coordinate system, which I decided to use the Cartesian coordinate on this because there was no circular motion really. And the problem wanted us to solve this using kinetics, and so looking at my free body diagram, I could write a force equals mass times acceleration equation in the x direction and the y direction for this problem. And so if we do that in the y direction, we know that there's no acceleration in the y direction because the car's just flat. And so we can find out that the normal force is just equal to mg. And then in the x direction, we have the force of friction to the left, and we know that the force of friction is mu times our normal force. And so using that, we can find out, and we can try and solve for mu, which once we find out mu for this problem, we can use that same value on the incline hill. And so using force equals mass times acceleration, we can create this relationship here. And then we needed to find acceleration in the x to be able to find mu. And so using our equations for constant acceleration, we can find the acceleration in the x direction. And so that's just me. This is the equation I used. Plugging in the given information from the problem was right here. And then that's what we find for the acceleration in the x direction. And so plugging that in, we find that our coefficient of friction, or mu, is 0.1533. So once that's done, we can turn over to the car once it's on an incline up the hill. And looking at this, we can draw another free body diagram that explains this situation. And this time I tilted my axis a little bit to make it easier. And then it was a matter of repeating the same steps we did in the first part on flat ground, but this time we have a tilted coordinate system, and so we're going to have to use that angle. And so this is the equation for the forces in the x that I created, and then this is the forces in the y. And the sum of the forces in the y just tells us that the normal force is equal to mg cosine of our angle 2.7. We can tell that angle from looking at our diagram here. And then taking that, we can plug that into x here. And we also know mu, and so we know that the force of friction is mu times our normal force. And so replacing that, and then replacing our normal force from what we found in the y direction, we have this equation, and that equals mass times acceleration in the x direction. And so taking that, we can solve this problem. We know that the masses cancel because there's a mass in each term, so we don't actually need to know the mass of the car. And plugging in all of that, we can find the acceleration of this car, or I guess I should say deceleration because it's stopping, is right here. And then what the question wanted us to find was the distance. And so now that we have the acceleration, we can go back to that same kinematic equation here and plug in what was given in the problem. So the final velocity was given, or we can figure out that that's 0 because the car came to a stop. The initial velocity was given, and our position is what we're trying to find. And so we plug in the acceleration that we found and then solve this equation for our final position on the incline, and it comes to 48.32 meters. And so that's the answer for this question.